For over 2 centuries, these iron beasts roared across continents, forever reshaping the world we live in. They were powered by nothing more than fire, water, and pure engineering genius.
But deep inside this rumbling metal monster hides a mechanism so elegant, so ingenious.
Today, we're not just looking at a machine. We're going to open its heart.
So how do you get 100 tons of steel to move? It all starts with a simple, powerful idea.
At its core,
This fire isn't just for show. It's generating an incredible amount of heat. And that heat travels through dozens of pipes,
which run directly through a huge tank of water called the boiler. This is high-pressure steam, trapped and compressed, building up immense force. Steam is just invisible pressure, really.
But when you harness it, when you control it, it has the power to move mountains, or in this case, a 100-ton machine.
it's this contained energy that becomes the lifeblood of the engine. Let's break down the engineering magic, piece by piece.
First, you have the firebox, the engine's stomach.
This is where the fuel burns, reaching temperatures hot enough to melt steel. That intense heat is channeled through long tubes that snake through the boiler. Think of the boiler as a steam factory. It's a massive, reinforced tank holding thousands of gallons of water.
As the hot gases from the firebox pass through the tubes,
the water surrounding them absorbs the heat and starts to boil violently, creating a massive volume of steam.
The pressure inside builds and builds, like a giant metal kettle ready to explode. But before that steam can be used,
it passes through a steam dome on top of the boiler,
which acts as a filter, separating out any water droplets. You want pure, dry steam for maximum power.
Now for the heart of the motion, the cylinders and pistons.
This clean, high-pressure steam is piped into a cylinder, where it pushes against a piston.
this single push is the fundamental action that drives the entire locomotive. But one push isn't enough. A clever device called a valve then redirects the steam to the other side of the piston, pushing it forward again.
This back and forth motion happens multiple times a second. This piston is connected to a long connecting rod,
which in turn is attached to the giant driving wheels.
powerful rotational movement that turns the wheels and propels the train forward. And what about that iconic chuff 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 sound? That's the exhaust.
After the steam has done its work pushing the piston, it's released up the chimney.
This exit creates the rhythmic pulse that we all associate with a steam engine. It's the sound of the machine breathing.
But with all that power driving the wheels, why don't they just spin uselessly on the track? Early engineers faced this exact problem.
Their solution was brilliantly practical. Easy now, lower it steady. Watch the alignment on the bracket.
Creating the friction needed for the wheels to grip. It's low-tech but incredibly effective. Next, look closely at the wheels themselves. You'll see massive pieces of metal on the opposite side of where the connecting rods attach. These are counterweights.
The powerful back and forth movement of the pistons and rods is violent and unbalanced. Without counterweights, the train would shake itself apart.
Finally, the connecting rods link all the driving wheels together, ensuring they rotate in perfect synchronization.
It's an engineered harmony,
that turns raw power into controlled forward motion.
Now, we've talked about the power, but what about the danger? A steam engine is essentially a bomb on wheels.
One mistake in managing the pressure, and the boiler could rupture.
That's why every sound you hear on a steam engine serves a vital purpose. Those loud hisses you hear when it's stationary?
That's likely the safety valves.
If the pressure inside the boiler gets too high, these valves automatically open to release the excess steam, preventing an explosion.
The engineer might also intentionally use a blowdown valve,
which shoots out a dramatic cloud of steam and hot water from the side of the engine.
This isn't for show. It's to purge impurities and sludge from the boiler water, keeping it clean and efficient.
And of course, the iconic whistle isn't just for signaling. It's powered directly by that same immense steam pressure. A voice for the giant.
Behind the scenes, the fireman and the engineer work in constant partnership.
A delicate dance of adjusting the fire and the water level to maintain the perfect balance between power and safety.
But here's the twist you might not expect.
Steam engines aren't just machines. They breathe.
They hiss. They pulse with a life of their own.
They feel less like an assembly of parts and more like a living organism.
And the whole system can collapse.
The engine's sounds tell a story to the experienced ear. The rhythm of the exhaust and speaks of its speed.
The hiss of the valves whispers of its pressure.
And the glow of the firebox reveals its inner fire.
It's a system where every component is critically dependent on the next. It's a perfect symphony of physics and mechanics.
The next time you see a steam train, remember that inside that metal giant is an orchestra of fire and pressure, of heat. And the whole system can collapse.
If you love uncovering the hidden genius inside incredible machines,
Subscribe and join us for our next investigation.